Ladies and gentlemen, I have the pleasure to present you the work entitled Light Yield Measurement of the Cerium Activated Lutetium Aluminium Nanopowder Garnet Scintillator. This work deals with the characterization of new scintillators in forms of nanopowders being developed in our institutions under our research and development project. So, here we present the preliminary result of the characterization of a new nanopowder scintillator, which is the Cerium Activated Lutetium Aluminium Garnet Scintillator. And we used alpha particles as a source of excitation, and we used the comparison method for the determination of the light yield of the prepared nanopowder scintillator. The Cerium activated nanopowder scintillator has been synthesized using the sol gel method, and the resulting nanopowder was compacted into a pellet of 1 cm of diameter and 3 mm of thickness, as shown in this figure. In the same figure, we show also the reference detector used for the measurement of the light yield. So the reference detector is the same material, which is the lutetium aluminium doped with cerium in form of single crystal, with the light yield is in the range of 12,000 to 15,000 photon per MeV. As measurement setup, we used a photomultiplier tube with the spectral response matches with the emission spectral of both detectors. Also, we used a linear amplifier and a multi-channel analyzer for the spectrum collection. So, the photomultiplier tube has been biased by an appropriate high voltage power supply. The gain of the amplifier was set at defined values for both detectors. The shaping time of the amplifier was set also at the minimum value, which allows the collection of the total charges created in the photomultiplier tube. This value allows also to collect the total charge created in the detector, as powder scintillators are known as high photon scattering and self-absorbing materials because of their opacity. This problem affects the efficiency of powders for gamma and X-rays. For this reason, we used alpha particles for excitation. This allows us to produce a high number of photons in the top layer of the material. And if we use the reflection geometry as shown here, the major fraction of the produced photons will be reflected to the photomultiplier tube. This allows the good measurement of the produced light and give rise to a good measurement signals. The relative light yield is calculated according to this relationship. The absolute light yield is given by the multiplication of the relative light yield by the absolute light yield of the reference detector. As results, and as we show here, the position of the full absorption peak of the reference detector is in the channel number 343.85. This value represents 100%. And the tested nanopowder scintillator shows a full absorption peak with the center is in the channel number 307.06, which represents 89.3 of the light yield of the reference detector. So, in terms of absolute light yield, and as we seen previously, the reference detector shows 13. If the reference detector shows 13,941 photon per MeV, this means that our prepared nanopowder scintillator exhibits 12,449 photon per MeV. And if the reference detector shows 15,000 photon per MeV, this means that the prepared scintillator exhibits 13,395 photon per MeV, as presented in this table. As a conclusion, in this work we obtained near 90% of light yield of the single crystal, which make our prepared scintillator as a good candidate to be used for different applications, replacing single crystals. And I thank you very much for your attention.